Thanks everybody for joining today's MagNetZ seminar. So today, I'm pleased to say that we have Kaixian from the Institute of Geology and Geophysics, which is part of the Chinese Academy of Sciences in China. And today he's going to be talking about the new Lord-Shaw method and how it can help us improve paleointensity estimates. So I will hand over to you, Kaixian, sorry.
Okay, yeah. Okay. Okay, thank you, Professor Greg, for your kind introduction. And I also appreciate Dan and other staff for their effort to organize such a great seminar. And this is Kaixian Qi, a PhD candidate from Institute of Geology and Geophysics, Chinese Academy of Sciences. And today I will talk about my recent study, which is aimed to find the reasons behind the biased results derived from the short-term method. And try to find solutions to address the issue. And this study received kind support from my collaborators at my institute, Culprit University, and Northwest University. And this is the outline of my presentation. First, I will give you a brief introduction of the short-term method. And after that, I will just describe my samples and workflow of the experiment. And finally, I will just show you the results and the new method. The precise retrieval of the paleointensity is essential for deciphering the dynamo processes and the planetary evolution. Several crucial topics, such as the solidification time of the Earth's inner core, interactions between different geospheres from the core mantle boundary to the atmosphere and the magnetospheres, can be answered by the paleointensity study. Consequently, several experimental protocols have been proposed to get the paleointensity data. Among them, the Taylor series method, which has a well-established theoretical basis, is by Louis Neal, is preferred for the thermal stable and non-interacting single-domain particles. But unfortunately, the samples adhering to these two prerequisites are very rare in nature. So we are still struggling to get enough authentic data to retrieve the paleointensity evolution. And this is a chart showing the frequency of the use of the paleointensity method. And the T-related abbreviation is the Taylor series method, and the S-related abbreviation belongs to the Shaw series method. For example, the S, LTD, DHDS, and SC here. What we can see in this plot is that the short-term method is another widely used protocol, second only to the Taylor series method. And in principle, the Shaw method can just avoid some of the problems that we may encounter in the Taylor series experiment. And from my point of view, there are at least 4 most influential papers that all published in GGI that in the development of the short-term method. So I will just introduce them one by one to introduce the context of the development of the Shaw method and raise some background issues. The original Shaw method was proposed by John Shaw in 1974, and is aimed to solve the problems rooted in the Taylor series method. We often fail or get unreasonable results in the Taylor series method because we have some non-single domain particles. And these particles have inconsistent unblocking and blocking temperatures. To solve the problem, John Shaw just proposed that we can use one single step heating above the Curie temperature and let the sample acquire a total TRM, and then compare the alternating field demagnetization spectra of the NRM and the TRM to get the paleointensity. Moreover, it includes 2 additional steps to monitor the thermal alteration, which is another troublesome problem in the Taylor series method. The AF spectra of the anhysteretic remanent magnetization before and after the heating were compared to select the unchanged coercivity range. And for example, if the slope of regression line of specific, say that in this coercivity range, there is minor thermal alteration, and we can use range to get our paleointensity data. And it's noteworthy here that this step of selected the unchanged coercivity range just implicitly contains the one important premise of the Shaw method, that the ARM should be an appropriate analog to the TRM during the heating. And bearing this in the mind, if the ARM is similar to the TRM, one can use the changes of ARM to correct the changes of the TRM during the heating. And this formula just express it in a mathematical form. The TRM and ARM1 and ARM2 here are the remnants at specific AF demagnetization level. And the TRM asterisk is the corrected TRM. And this is what Rolf and Shaw did in their 1985 papers, and they just get good result in their tested samples. And later, researchers find that both accurate and biased results can be derived from the ARM correction. And here is an example. We can see in the left sample, it has just a good paleointensity result, which is very close to the expected value of about 85 microtesla. But for the sister specimen, it just have about 40% bias. So there must be something different between the samples. And here are some plots. For the left samples, it's NRM versus TRM1 plot, and it's ARM1 versus ARM2 plots, just are very linear. And for the right samples, it's NRM versus TRM1 plot. It's obviously curved, but it's ARM1 versus ARM2 plots. It's quasi-linear. So at least for the right sample, the ARM is not a good analog to the TRM. So it's not surprising to have a biased result in these samples. To address these issues, Tsunakawa and Shaw in 1994 GJI paper just add 2 additional steps to test the efficiency of the ARM correction, which is called the double heating technique. In their paper, they just heat the sample again to acquire a second TRM, and and then they just AFD magnetize it, and then they just let the sample to have a third ARM and called ARM3 and AFD magnetize it. And use this data, we can have a similar TRM2 correction data, and we can draw a plot that is TRM1 versus TRM2 correction. And use this plot, we can estimate the known lab field if the retrieved result is close to what we set the is close to the strength of the lab field. We can see that the ARM correction is efficient, so we can just adopt the sample's paleointensity estimations. And later, Yamamoto et al. Just add additional low temperature demagnetization steps after each remnants acquirement step to further mitigate the MD effects. And also, he just changed the denotion of the ARM to ARM0, ARM1, and ARM2, which is slightly different from the original definition in the former papers. And he just get good result in the Hawaii 1960 lava flows. So everything seems to be perfect now, and we should get accurate results if samples can pass all the selection criteria. However, the left plots show Hawaii 1960 lava flow samples, which has a great linearity in its NRM versus TRM1 correction plot, and it can pass all the selection criteria currently used. But its paleointensity estimation is much higher than what we expected. So what's caused this bias? There is one thing to be noticed is that its NRM versus ARM 0 plot has a very similar shape to its TRM1 to its ARM1 plot. And this shape similarity will just cause a linearity in its NRM versus TRM1 correction plot. Besides, we know that the lab field is very close to the expected field strength. So if the ARM is a good analog to the TRM in this sample, this curve will be just steeper like this. So we just have a speculation that we just have two curves here with very similar shape, but the integral efficiency of its TRM to ARM is quite different. So we can just have an erroneous line here, but with a biased result. So we just have this speculation and want to validate it. And we just do a pseudo-Tsunakawa-Shaw experiment to see what will happen. And this is our samples. We use the basalts drilled from the Tarim large igneous province with an age of about 289 MA. And we just drill and cut the samples into small pieces to get more specimens. And in total, we have 97 specimens from 13 samples. The rock magnetic experiment on sister specimens show that the PSD titanomagnetites are the dominant remnant carriers in the samples. And also, there is a large difference before and after the heating. So the sample are very prone to thermal alteration, which are suitable for the aim of this study to determine the controlling factors of the biased results. And this is the workflow of our pseudo-Tsunakawa-Shaw experiment. We first heat the sample to 610 degrees Celsius, and we just use Tsunakawa-Shaw experiment protocol to retrieve this field. We also conduct hysteresis loop measurements before each heating steps to monitor the change of their rock magnetic parameters. After this, we demagnetize the specimens to further mitigate the effects of isothermal remanent magnetization. And we conduct the experiment in 3 different heating environments, that is air, argon, and argon with additional ion sheets to enrich the extent of the thermal alteration. After that, we just calculate the paleointensity and compare them with rock magnetic parameters. And we adopt several different selection criteria currently using to evaluate the effects from the criteria. We also define some rock magnetic parameters to describe the changes during the heating. And we can see the LTD here is the remnants loss in the LTD treatment, and MDF here is the median destruct field, and R here is the efficiency of TRM to ARM. And the A and B here, it just denote after and before the heating. And the X here just denote the round of the heating numbers. So let's come to the paleointensity results. And we can see results from criteria 1, 2, 3 all yield mean paleointensities consistent with the expected answer of 20 microtesla within 2 standard deviations. But none of them are within 10% of the expected value. So we can see the large standard deviation here for the criteria 1 and 2 are due to the large numbers of biased results. And the most strict criteria 3, which is more widely exploited in the Tsunakawa-Shaw method, just filled out the majority of severely deviate paleointensity results. And it just demonstrates the usefulness of the double heating technique. But it reduced the accepted data set significantly and still result in a mean paleointensity with about 12% underestimation. And the result passing the criteria 3 are too limited to facilitate meaningful statistical analysis. And we only use the results from criteria 1 and 2 for further discussion. And here are some represent results from the different section criteria. And we can see here are the different rock magnetic parameters. And among the rock magnetic parameters, changes in the TRM to ARM efficiency have the strongest correlation with the paleointensity result. And this is consistent with our above mentioned speculation, and indicate and also this result were from the criteria 2, and also the criteria 1 have a very similar results of to the criteria 2. And this indicate that if we only check the linearity of the NRM to TRM1 correction plot, may be a little bit hazardous, since the culprit of the biased result seems to be the integral change of the TRM to ARM efficiency. Furthermore, let's go back to the calculation equation. If we just assuming a good linearity in its NRM to TRM1 correction plot, the formula will be changed in this form that the paleointensity estimation should be positive correlated to its R before and after the heating. And for example, if the R after the heating just become smaller, and it will just give a this paleointensity estimation will just be higher, just like in this area. So we know that the culprit of the is the change of R during the laboratory heating. So what leads these changes? And let's go back to the initial state of the samples. These two pictures shows the relationship between the paleointensity results and the hysteretic parameters. It's interesting that besides some single domain like samples, other data have a very good correlation in this plot. And for samples which have a intermediate hysteresis parameters, it's more likely to have a accurate paleointensity estimation, unlike it is severely altered, denoted by the blue dots here. And moreover, we just can see the such correlation more evidently in its initial R and paleointensity result. And also, we can see a wave shape in its delta R and initial R plots. So all these characteristics indicates the grain size changes of the magnetic minerals should play an important role in these issues. This is the R versus the magnet grain size plot. And we can see here is here two dotted lines are the R value of 2 and 2.5. If the sample have a total R value below 2, it means it R will just increases when the grain size decreases, and it will just get an underestimation. And if the R is between 2 and 2.5, it will just have a stable plateau. And also, the larger particles here will just have an increasing R, but the small particles here will just have a decreasing R. So it may just have a equilibrium. And for the smaller particles here, which have an initial R larger than 2.5, because the size is just close to 200 nanometers, and its R will just decrease it sharply along the reduction of the grain sizes. So this relationship is quite consistent to what we see in our results. And this is further demonstrated by the microscopic observation and the KT curves. We can see here in a TM observation, this is a homogeneous titanomagnetite, and after the heating, it will just oxy-exsolve to ilmenite and titanium pore magnetites. And also we can see this trend in their KT plots. And for the larger particles, we do not see any changes. So all these observations are, oh, I forget to mention one thing. This grains is quite small. It just have size about several hundred nanometers. And this observation is quite consistent to what we see in our result. So we have demonstrated that the changes of R is caused by the reduction of the grain sizes of the magnetic minerals. And this is a midway summary. And we just find that the changes of R just during the heating is the culprit of the bias result in the shell tap method. And since the currently used criteria only examine the linearity of the NRM and versus TRM1 correction plot, and it will just ignore the effects of the proportional changes in R. And furthermore, we find that the grain size reduction is just the cause of the changes in the R. And because there is a non-linear relationship between the R and the grain sizes, some samples with dominant grain sizes of about 200 nanometers are more likely to suffering from the issues and may produce more biased results. And let's come to the last part, the new method. And you may remember this formula that we mentioned formerly. The slope of the NRM to TRM1 correction plot just equals to the R before and after the heating multiple our lab field. So if we have just a equivalent Asian field and lab field, this ratio will just close to 1 and will indicate an unchanged R ratio and also the accurate paleointensity. But we didn't know the Asian field, and in most cases, the lab field is not equals to the Asian field. So we cannot determine the unchanged R directly. So are there any ways to solve this problem? There is two bias result in our experiment. And after the ARM correction, we can see that both of the NRM to TRM1 correction plot just show a S shape. And for the more biased samples, the distortion are much evident. So maybe this difference can help us to solve this issue. First, let's consider some simple and ideal case. We just simulated some result from more MD-like to more SD-like samples, and we assume that the heating can just change the state of the samples from more MD to more MD from more MD to more SD state, and we can get several NRM versus TRM1 correction plot. The most ideal case is the state 1 to state 1, and it's just have a perfect line and have an unchanged R during its whole coercivity range. And for the worst case, it's the state 1 to state 5. It has more distortion and have more biased result. So remember this formula that the paleointensity estimation is proportional to its R before and after the heating. So we can just do the linear regression at different cutoff coercivities. For example, we just use the first point cutoff and we have the paleointensity from this from the slope of these regression lines, and we have the R before and after heating of these squares. So we can just have a regression line denoted by these black dotted lines. And after that, we select another cutoff coercivity here, and we can get another line here, which is the dark gray lines. So we can have many lines like this, and just we have some intersection points. Because the most ideal case, it will just have a constant R with its whole coercivity range, like here. So all these lines should be centered around the unchanged R before and after heating and the true field intensity. So we can just use this way to calculate the accurate paleointensities. And also, you may notice that there implicitly contains an important premise, that is the changes in the R before and after heating should also be proportional, or in a more simple expression, the distortion of the NRM versus TRM plot should be consistent at different cutoff coercivities. So if this is true, we can just use another way to get intersection points. Just use the R before and after heating baseline, and R before and heating of other coercivity of other cutoff coercivities. And also, since some curvature in these lines will just affect the intersection points, we need extra checks for the curvature. And this is the examples. And for these two results, it just passed the curvature check. And for these two results, because it has a curvature in its regression line, and will just cause bias for its intersections. So we just reject them. And also we introduce an error check, which means that the difference between the difference between the slopes of the two regression lines need to be larger than the maximum of their regression error. And then we just applicate this new method to different data set. This is the some of the result, and we can see that the load-show method just have more accurate result compared to the formal calculation ways. And the R check has the use of this R versus R check has better performance because it directly examines the curvature of the it just examining the curvature in the core premise of the load-show method. And we get just accurate result in 8 of the 12 data sets. But we still have some poorly performed result in some of the data sets. So what caused this failure? We just examine our data and find that is a similarity in their delta R before and after heating versus R before and after heating baseline plot. And it means that the result can just deviate on both sides of the true value. It means that the result can just deviate in the same direction on the both sides of the true value. And this plot just illustrated because it can, this is the unchanged R and the accurate paleointensity point, and it will just have the same changes in both sides, and some minor curves in this data will just introduce very large bias in the intersection points. So all these data have these problems. To solve these problems, we use this function to fit the data of the delta R before and after heating and R before and after heating baseline data. and substitute the abscissa of this to the baseline regression line to get the paleointensities. And with this curve fit method, we just have we just yield accurate result in all of the test data sets. And this is the take-home message. And we just find that the culprit of the bias result in the Shaw method is the changes in the R during the heating caused by the changes of the grain sizes of the magnetic minerals. Also, we use a new calculation method called the low-Shaw method, and we just get accurate result in the tested data sets. But there are still some questions for further exploration that we may use data from the NRM to TRM2 correction plot for supplementary calculations and comparisons. Also, we need to propose more quantitative criteria for certain procedures, such as what is the number, list number to determine the accurate intensity, and also the selection of the baseline. And also, we noticed that some of the data is very curved in their NRM to TRM correction plot. If we can use this data, it will just make the successful rate more higher in the applications. And this is my presentation, and thank you for your attention. So yeah, that's all.
Thank you very much, Kaixian. That's a really interesting talk. I think we can all give him a virtual round of applause for something a really interesting talk there. I can open the floor to questions. So if anybody has a question, you can use, excuse me, you can use the Zoom raise hand function. So I will actually jump in with I'll jump in with one of maybe a couple of questions if no, while everyone thinks of their own. You through your experiment, you were measuring the hysteresis parameters after every stage. Have you have you looked at, and maybe I missed it in the plots, but have you looked at how the hysteresis parameters change after each heating step and how that relates to the change in R?
It's not very good. May I beg your pardon?
Yeah, no, sure. So have you looked at how the hysteresis parameters change after the heatings
They
and
all just yeah.
how that correlates to the change in R?
Actually, all the samples become more SD-like as I didn't show the plots here, but their hysteresis parameters just I mean go for example for the squareness it just go higher, and for all the samples. So we think it's just means the grain size of the magnetic minerals just have been reduced. And we didn't compare the changes of the hysteresis parameters to the R. But I think they will just show a positive correlation, because we can see in these two plots, they just have very similar trend besides these SD-like samples. So I think they will just have a positive correlation.
Yep. So Andy Biggin has his hand up for a question. On you go, Andy.
Hello, trying to make my video come on. I don't think it seems to be working. But anyway, hi Kaixian. That was a great talk. Really nice set of results you've got there. So yeah, I have a question about just real samples and overprints. So how well how would your method be affected if you had if you're struggling to isolate the overprints? Also, yeah, I guess there's also the problem of some samples you can't fully demagnetize with AFD-mag as well. So I was wondering if you comment about the general applicability of those.
Yeah, yes. Thank you, Professor. And yeah, We have used some modern lava flows as our test data set, and like this is the samples from the Sakurajima volcanoes. Actually, we just select the characteristic components that's from the I think it's 18 micro Tesla. 18 millitesla coercivity to its maximum AF demagnetization, and we can have some good result here. But yeah, actually you are right, and I also mentioned in the last part that this is our selection of the baseline. In current paper, we just use the maximum fraction of the character that has very seriously overprint. The character component may be the fraction of the characteristic component may be quite less. And also, we note that the noise in the higher AF demagnetization level is quite large, and it will just affect the processes we find the intersections. So we are currently trying to solve these problems. Yeah, this is for the first question. And sorry, I forget your second question.
Oh, just about, I guess if you've got samples where you can't remove, all of the remnants by AFD mag, do you then subtract away, I guess, what's the residual?
Yeah. We just subtract the remnants after the maximum AFD, and we just use for this study the maximum AF peak field is 150 millitesla, and we just subtract the remnants that are higher than this peak field, and we just focus on the coercivity range between 0 to 150 microtesla
Okay.
or millitesla.
Great,
Yeah.
thanks. I'll have to let John Shaw know that he's now a lord. He'll be very pleased about that.
Yeah, and this abbreviation is inspired by Professor Yamamoto. Yeah.
Thanks very much, Andy. It does feel like a very much a Yuji Yamamoto style of name, and John Shaw will definitely appreciate it. Simon Lloyd, you have a question?
Yeah, hi. Really nice talk and a really nice study, so thanks for that. Yeah, it looks like this initial R0 is the really important thing that we should be looking at initially. And so we could even go back and sort of, look back at experiments that we've previously done and, analyze those again with that in mind, maybe. I don't know what you think about that.
Sorry, I think I missed several words in your sentence. Yeah, so
it's okay. I've got another question about the selection criteria plots.
Yeah.
Yeah.
Please?
So yeah. So I just wondered, the criteria 2 looks like it does quite a good job, to be honest. And I do wonder, like I have wondered in the past about the double heating technique, how useful it actually is. Because I can see you've got one extreme outlier there. I just wondered, without that, I think that second selection criteria does a pretty good job. What?
Yeah. I think this is what you mean in your 2021 paper. Yeah. Actually, yeah, but you can see the averages between this all these selection criteria are quite similar and are all close to the expected value. But we can see in the criterion 2, it just includes some more some more biased result, but it can just still get the good good means. And for the results passing the criterion 3, which is the double hitting technique, it will just largely shrink the data set, and also it just also includes some slightly biased samples, and have a averages and have an average close to this. So if I think if for you have a large data set or large number of samples, you may I think maybe the criteria 2 will just work better, because it will just get more data, and actually because the successful rate of the criteria 3 is quite low. If you have some very non-ideal samples, you may have no results. And this is just the case for my NRM results of this tarim basalt. So I just find for some solutions. Yeah, and actually, it's very interesting that I have tried the Lord-Shaw method, and the result passing the criteria 2. They are just very close. So yeah, maybe you are right. Yeah.
I think the double heating technique, so that extra criteria you've got, I think because that is so sort of non-unique, so you know, you can get different values if you take the samples out of the oven at different times. So I think that needs to be relaxed, and then look at the data again and see what it does with a more relaxed criterion. And also about the plots below them, you've got these curves early on, but I noticed you mentioned about time delays in your measurements. So I wondered, you know, theoretically, you should be able to take that whole coercivity range, but obviously you're getting a viscous component early on. Is that right?
Yeah, it's right. And we can see in this plot, this is well, because we just the total measurement time for such as the ARM0 or ARM1 will just take about 2 hours, and for some very MD-like particles, it will just have enough time for its remnants to decay. And we just test this effect, and the sample here is more MD, and the sample here is more SD. And we can see for the MD samples, it will just lose its remnants about 10%, but for the SD samples, it will just keep stable. And we also have some other evidence that we can see if we just use the full coercivity range to get the baseline regression. We will just have a erroneous value of the paleointensity when its R before and after heating equals to 1. But if we just use a 6 millitesla cutoff, it will just be more close to the expected value of 20 microtesla. So we think it's more reasonable for us to select about 6 millitesla cutoff for the paleointensity determination.
Yeah. Okay, just one quick comment about your new method. How many extra steps is it compared to a normal Shaw method?
Actually, there is no changes in the experimental protocols. We just use the same steps, but use different use different calculation ways. And actually, the exact number of the results we need to get reasonable intensities is a little bit weak now, and we just explore explore these parameters in our recent studies. Yeah, and I also mentioned it in these questions. Yeah.
Thanks.
Excellent. Thanks very much for a series of questions there, Simon. I think we'll have to stop there for questions today. So I think we can all give Kaixian another virtual round of applause for a really good talk and handling Simon's questions really well. So thank you very much. Before we all finish off for today, just a reminder that MagNetZ, all of this video will be recorded and put onto YouTube, and there you can see all of our other MagNetZ seminars of the series. We'll be returning in a few weeks in late July for our next seminar, but we do have a couple of slots still open in August. So if anybody is interested in giving a MagNetZ seminar, please reach out to myself or the MagNetZ team and we can arrange a slot for you. So thank you everybody for joining MagNetZ, and we'll catch you next time.